So, welcome to the next exercise, or the next practical class about density measurement. And first of all, I want to talk about what is density. The density is usually in physics indicated by the Greek letter rho. That is, stands for an R in Greek. And the density is defined as the mass of an object divided by its volume. Now, since we want to express everything in SI units, we have to think about how to express the density in SI units. We express the mass in kilograms. We express the volume in cubic meters, because meter is the SI unit for the length. And therefore, the density has the units of kilograms per cubic meter. As you know, you all know this quantity of the density, and you all know the density of water. Usually, the density of water is given as 1 gram per cubic centimeter. This is, of course, not in the SI unit, or as a derived unit from the SI unit, however, not really expressed in the base SI units. So in order to convert it, we have to replace the gram by the kilogram. And 1 gram is, of course, 1,000th of a kilogram. And the centimeter is 1/100th of a meter. So therefore, we have here to write 1/100th of a meter to the cube, because here we have also the centimeter to the cube. So now we have just to do some algebra. So 1,000, we could also write it here into the numerator. The denominator is 1,000. And we have to put here both factors to the power of 3 times 1. And if we put 100 to the power of 3, then we are at 1,000,000. So with 6 zeros, and we have here a cubic meter, and here is a kilogram. Now we can cancel here 1,000 with 3 zeros here of this million, and then we have here the 1,000th is here in the denominator. We can put it into the numerator, and we arrive here at 1,000 kilograms per cubic meter. That is the density of water expressed in base SI units. It always sounds very large. However, this result makes perfectly sense, because we describe here how big is the mass of water if we take 1 cubic meter of water. And 1 cubic meter is 1 meter in this direction, 1 meter in that direction, and 1 meter into that direction. And you know from everyday life that it's really, really heavy. And so far it makes sense that we arrive here at a density of 1,000 kilogram per cubic meter. So that is rather typical. We can also compare the density to other densities of other substances, for example, for solids. We have aluminium. That is here also the density in kilograms per cubic meter. So then for aluminium, we have 2,700 kilogram per cubic meter. For iron, we have a density of 7,860 kilograms per cubic meter. For gold, we have a density of 19,300, so about 20 times larger than that of water. So therefore, if you ever watch a movie like where they carry a box of gold, it's for any person it's virtually impossible to carry really a box of gold because it's so heavy you can't carry it. So therefore, and then we have other liquids. Water is the standard substance, that is 1,000 kilograms per cubic meter. So this unit here also extends to down here. Then we have blood. That is 1,060 kilograms per cubic meter, so slightly higher than water. Alcohol is 806, and carbon tetrachloride is, that is CCl4, that is 1,587. So you see here, compared to the solids, liquids are much lighter. They all range in the region of 700 to 1,300 kilograms per cubic meter. And therefore they are typically a factor of 5 to 10 smaller than that of solids. What is interesting to compare with are gases. Again, we have expressed this in kilogram per cubic meter, and then a gas like air has a density of 1.21. Oxygen has a density of 1.43. CO2 is definitely much higher, 1.98. And H2, so hydrogen, has a density of 0.09, so much lighter than the other ones. So what is the reason why I write this is you see here from these numbers here that gases are typically a factor of 1,000 lighter than liquids. So they definitely have also some mass and some density. However, it's typically on the order of 1,000 times smaller than that of liquids or solids. And the reason is that in a gas, atoms are much more separated, and therefore the density is lower. So here for this experiment, we need another quantity, and that is the pressure. So, the pressure is defined as the quantity P, force per area. And the units of the force is in Newton, and the area A is expressed in square meters, and therefore the unit of the pressure is Newton per square meter. And this has a special name. The name here of this quantity, Newton per square meter, is also called Pascal. Named after Blaise Pascal, who was a famous mathematician, physicist, theologian, philosopher. So he extended over a broad range of different topics. The Pascal is rather small. Our atmosphere, so our surrounding air pressure here, of one atmosphere is 101,325 Pascal. So this demonstrates nicely that this is a very small unit. Or as an alternative unit, we oftentimes use the bar. And the bar is 100,000 Pascal. And therefore we can also write that 1 millibar, which is a thousandth of this, is 100 Pascal. And for 100 Pascal, we also say typically 1 hectopascal. So in the weather report, when they changed from the bar, so in the old days, the weather guy reported the air pressure as so and so many millibars. When they switched to SI units, to the Pascal, they simply switched from millibar to hectopascal, and everything else was identical. So this is hectopascal. So there's also an old unit which is very often used in medical sciences, and that is 1 millimeter Hg. That is, for example, used by medical doctors if they measure your blood pressure. And then if you are lucky, and if you have good blood pressure, then it says you have a blood pressure of 120 to 80, and so that's wonderful. And that means really the systolic blood pressure is 120 millimeters Hg, the diastolic blood pressure is 80 millimeter Hg. And this is oftentimes also called 1 Torr, named after Torricelli, who was an Italian physicist, and that is 133.3 Pascal. Or we could also say 1 atmosphere is 760 Torr, or millimeters Hg. So here for our experiment, we try now, the goal is to measure the density of some objects, and we measure this density of the object with Archimedes' principle. And in order to understand Archimedes' principle, we have to first introduce a quantity which is based here on this pressure, that is called the hydrostatic pressure. So let's what is hydrostatic pressure all about? Now you have all experienced the hydrostatic pressure when you are diving into a lake or an ocean or in some swimming pool. Then you realize that if you are diving into the water, the pressure inside this liquid, so this is here, there's some column of water, maybe a swimming pool, and you are diving here into this water, and this water or this liquid has a density rho, and when you dive into this liquid or fluid, then the pressure increases as you go deeper and deeper into the liquid. And if we calculate now the pressure here at the bottom of this container here, the container might be filled up to a height h with this liquid, and it has here an area A. Then we can calculate now here the force onto the bottom of this container. So the volume of this liquid is, or let's say the volume of the fluid here is the height h times the area A. And the mass of the fluid is now, with our definition of the density, is now rho times volume, because the density is defined as mass over volume. And that is going here into this equation. We can express here the mass of the fluid as rho times the volume. Now we can put this equation here, and at this point here, then we have the density rho times h times A. That would be the mass of the fluid here inside this container here. Now we want to calculate the force which this fluid puts here onto the bottom of this container. Now the force of the fluid is now m times g, mass times gravity. So this is the mass of the fluid times g. That is the gravity. Because that is here the simple usual equation for gravitational forces. Now we can put here this expression into our expression for the force. So that is rho times h times A times g. Simply replaced here this m fluid by this expression. So that is the force which this column of water or fluid exerts here on the bottom of our container. Now we want to calculate the pressure here at the bottom here. Now the pressure is, by the definition of the previous page, that is force divided by area. Now we can put here this expression here into this expression here, and then we get rho times h times A times g divided by A. As you can see here, this capital A, the area, cancels here, and therefore we get here rho times h times g. And this here is called, let's write this separately. The P fluid is equal to rho times H times G. That is called the hydrostatic pressure. So in addition to the pressure due to the liquid, we have here also some pressure of the air, PL, that's the external air pressure. So the total pressure is P, that would be the air pressure, plus the pressure of the fluid. That is PL plus rho times H times G. So that would be the total pressure at the bottom for at the bottom of this column of liquid as a sum of the air pressure plus the pressure of the liquid, the hydrostatic pressure. As an example, we can now calculate the hydrostatic pressure of a column in some depth. So let's hydrostatic pressure in water at a depth of H equal to 10 meters. So 10 meters below the surface. So the pressure of the water is rho of the water times H times G. So now we know that the density of water is 1,000 kilograms per cubic meter. We want to calculate now the pressure at a depth of 10 meters. And the gravity is, as usual, 9.81 meters per second squared. So first we multiply 1,000 times 10 times 9.81. That's 98,100. And then we have to care about the units. What we see here, the meter cancels here with the meter. And otherwise we have here kilogram per cubic meter times second squared. So the do I have to? No, I did a mistake here. Meter here, this doesn't cancel here. This gives here meter squared. Doesn't cancel here. This was a mistake here. Doesn't cancel. We get a meter squared. So therefore, we can now write here 98,100 kilogram times meter divided by second squared, and here is still a meter left here divided by cubic meter. Why do I write it here in this funny order? Because we can identify this as a Newton. And here, this one is 1 over square meter. So in total, we get a 98,100 Newton per square meter, or 98,100 Pascal. That's the reason why I wrote it here in this strange fashion. And that would be also, could also be named as 981 millibar, and that is close to 1 atmosphere. So that means at the bottom of some lake or some swimming pool at depths of 10 meters, the hydrostatic pressure corresponds roughly to 1 atmosphere, and therefore the total pressure at the bottom of this swimming pool or pond is 1 atmosphere from the hydrostatic pressure plus 1 atmosphere from the air pressure, in total 2 atmosphere. So that is the introduction to this experiment, and in the next video I will explain Archimedes' principle, because Archimedes' principle is based here on the hydrostatic pressure.